The Cadence AWR software suite includes several tools. In most of my previous videos, I have used Microwave Office, which is the circuit simulator. But within the AWR environment, there is also another very powerful tool called VSS, which stands for Visual System Simulator, and allows you to model complete communication systems. In this video, I will first start by looking at a simple sinusoidal signal, using the familiar Microwave Office simulator, and then I will demonstrate the differences between Microwave Office and VSS, when working with a signal of this type. Indeed, when we analyze linear circuits, we work in a sinusoidal steady state, and the first thing we often do is add a sinusoidal source to a circuit schematic. We then set its amplitude. In this case I am keeping the default value of 1 volt peak, which is 2 volts peak to peak. And then also set its frequency, which can be done globally, or individually for each schematic, as I am doing here. We can then add a load resistance, place a probe on its upper terminal, and set up a new graph to display the voltage waveform. To do this, we just use a V-time measurement. This will automatically display 2 periods of the waveform based on the frequency specified for the schematic. Let's also change the y-axis range to display the waveform a bit more clearly. This waveform looks perfectly continuous, but, in real life, when we measure a signal with a digital oscilloscope, we will have a finite number of points. The waveform may look continuous if the sample points are very closely spaced and we linearly interpolate between them. If they are not so closely spaced, we can use sin x over x interpolation, and this is often done by default anyway, and hey presto, we have a smooth waveform. But this just masks the reality of having a finite set of sampling points. In any digital system, continuous signals are sampled using an analog-to-digital converter, ADC for short, and that's unavoidable. Digital communication systems are no exception. Indeed, VSS models realistic communication systems, and this is why it is a sampled, time-domain simulator that uses a fixed time step between samples. So when we generate a sine wave in VSS, depending on how we sample it, we may end up with very different graphical representations. Let's make a start. We first create a new system diagram and place a sine block on it. Next, we need to specify which type of signal it will generate. This may be confusing at this stage, but we will explain the different signal types in VSS in due course. For now, simply hover over this right-pointing triangle, double-click on it, and select Real as the signal type. This is the type of signal that most closely aligns with the ones that you are familiar with. You can see that the triangle has gone from transparent to yellow, indicating that the output signal type of the block has now been set to Real. Note that this simulation will not run unless we perform this step. Unlike in Microwave Office, both the amplitude and frequency of our sinusoidal signal are set directly in the sine block. Let's set the tone's frequency to 1 MHz and its peak amplitude to 1 volt, which is 2 volts peak to peak. Now we can add a test point and connect it to the output of the sine block. A test point in a VSS system diagram is similar to a probe in a Microwave Office schematic. Now comes the crucial step: setting the sampling frequency for our system diagram. We must do this correctly before we carry out any measurement or plot any waveforms. Note that there is an oversampling parameter here too. This parameter does not change the sampling frequency and, in this context, it does not matter at all. We will discuss its significance in subsequent videos, and for now, we will just set it to 1. Well, we have a frequency of 1 MHz, so what's the minimum sampling frequency we need to reconstruct our signal? If you said 2 MHz, based on the Nyquist theorem, that's not a bad guess, but let's see how things play out if we do that. Let's create a new rectangular graph and add a waveform measurement to it. Ensure you select the type as Real. Now let's change the time span of the measurement here so we display 2 periods of the waveform. The period of a 1 MHz sine wave is 1 microsecond, so let's set the time span to 2 microseconds. And run our VSS simulation. As we could anticipate, we get 2 samples per period. And we can see their exact location by adding markers to the trace from the plot settings. Let's also change the y-axis range to make these points more visible. Lastly, let's change the x-axis start to be relative to the left edge, which will make it easier to read the time step between sampling points. VSS does not interpolate between samples. It simply joins 2 consecutive points with a straight segment. Conveniently, those samples happen to be aligned with the maxima and minima of our sine wave, so we are kinda getting the amplitude of the sine wave right. But that's just a bit of luck. If our virtual ADC started sampling at a different amplitude point in our waveform, we would get a different peak-to-peak amplitude. We can see this if we specify an initial phase value in the sine block and make it tunable. The sampling points in VSS remain fixed, but we are sliding the waveform back and forth past those sampling points, thus changing the amplitude at which we trigger the sampling. This also happens with a real oscilloscope. Here we've set the sampling frequency only slightly above the Nyquist frequency, and the scope, which is sampling in real time, triggers at slightly different instants on each acquisition, so it displays a different waveform every time. The Nyquist theorem specifies the minimum sampling frequency, but reconstructing the signal also requires the application of specific interpolation formulae. Practical systems can't sample at exactly this minimum rate. As we'll see in later videos, they must sample at a higher frequency and often use sin x over x interpolation because their sampling is pulse-based. Let's go back to VSS now and increase the sampling rate to 20 megasamples per second. This will allow us to collect 20 samples per period, which gives us a much better result. To observe how the waveform changes with the sampling frequency, we can gradually increase it and see the changes in real time. Instead of opening the system diagram settings every time we want to adjust the frequency, we can use a swept variable, together with the tune tool. We first declare a variable in the system diagram, and assign an initial value to it. Here I've called it fs. We then add a swept variable block. Associate it with the variable we've just initialized. And then specify the set of values that we want the variable to take. Next, we associate fs with the sampling frequency parameter of the sine block. This enables us to change the sampling frequency directly from the diagram and override any global settings. Lastly, we need to change the graph settings so that we can use the tuner to display the plot associated with each value of the swept variable. Now we can run the simulation again. And, as we increase the sampling frequency with the tuner, we can see how the resolution also increases. Note that, although the tuner shows only the array index corresponding to the swept variable's value, you can read the actual sampling frequency, in Hertz, down here. Now that we have taken the sampling frequency to 100 times that of the signal, the trace is much finer, and it will be even clearer if we remove the plot markers. Finally, what we can do is compare the sine wave generated with Microwave Office and the one generated with VSS. However, note that the sine block generates a cosine by default, whereas the ACVS block generates a sine, so we need to include a phase offset in either our circuit schematic or our system diagram to compare the two. Here, I have chosen to add a phase offset of -90 degrees to the sine block, so our VSS plot should now display a sine wave. I can copy this plot into the graph that I created earlier for the Microwave Office waveform to compare the two. As you can see, the agreement is excellent.